Our next presenter comes from one of our sponsors, Intel, Intel CTO of EMEA, Dr. Laurent Philippe. Welcome.
Thank you, Brian. I'm going to talk about what Intel makes possible for HPC and AI. The important thing, as we heard earlier today, is that the workloads need to execute well. And therefore, what we have decided to do with the Intel 4th generation Xeon, with the Xeon Max and with the data center GPU Max, is to look at workloads and find solutions that enable the best execution of them. That's why one size does not fit all. And actually, Xeon is capable of running a lot of applications, a lot of workloads, but then people want to have better performance. And depending on the workloads, you need acceleration of some type. The different types of workloads are, of course, as you know, compute bound, memory bandwidth bound, or a kind of mix of both, like intermediate. The idea is really to find solutions for executing all of them well. And you can have some that will be compute optimized, that's at the top, some that will be memory bandwidth bound at the bottom, and then on the left, some that are frequency optimized. That's what we try to do with Xeon Scalable processor and the 4th generation that has been introduced in January, codename Sapphire Rapids. And that's a continuation of the line of Intel Xeon processors. So they are capable of executing all of the workloads. But then if you have workloads that are memory bandwidth bound, then they will benefit from the Xeon Max, which is the second here in the middle. And then there are some workloads that are very suited to executing on a GPU. And that's the Intel Data Center GPU Max. As you know, we have been coming up with the one API standard that we offered, and that was, if I'm not mistaken, at Supercomputing 2019. At that time, we did the beta, and now we have some very good solutions that work across various types of architectures. Xeon, Xeon Max, FPGAs, GPUs. So that's very, very effective as a development environment to work with. Let's have a look at the new 4th generation Xeon Scalable processor codename Sapphire Rapids. It is bringing a lot of new features, a lot of accelerators that are actually integrated in it. Of course, you know of the AVX512 that you had in previous generation of Xeons. But we also have data streaming accelerator, which is used in Intel MPI. And because all the workloads are going to use, in some ways, AI, and we had a flurry of information about this over the past 2 days, Intel has integrated AMX, the Advanced Matrix Extension, which is a matrix multiply accelerator directly into the core. Instead of being working on, let's say, 3x3 or 4x4, it's working on 16 rows of 64 bytes each. So a kilobyte as a matrix. And you have enough registers to store 8 of those matrices. So that's pretty efficient for applications that are using int8 or FP16. And of course, because we want to make it easy for the users, we have integrated the capabilities that AMX are providing directly into libraries that are called in versions of TensorFlow or PyTorch that are upstreamed. So no need to change anything in the application, and you'll see the range of performance increase that we are getting through especially this AI accelerator. It goes up to 60 core, and it's on the latest Intel 4 manufacturing process. Goes with 8 channels of DDR5 4800 and PCIe Gen 5 and CXL 1.0. Compared to the previous generation of processor, the 8380, the Ice Lake, then you can see here on industry benchmarks that it's giving 40 to 60% performance increase. But what really matters is how it does well on real applications for the industry, real workloads. And across the range of applications that you can see here, it goes up to 2.6x the performance of the previous generation of Xeon processors. But as it's not enough for the applications and the workloads that are memory bandwidth bound, we have introduced at the same time the Xeon Max processor that was also back in January. Everybody knows the memory wall that we are facing with the applications, where the CPU performance is increasing and the memory capacity in terms of memory bandwidth per core is kind of stagnating. So the Sapphire with HBM memory that we have introduced is based on the Sapphire Sapphire that I have just talked about a second ago. And it adds 64 gigabytes of HBM2E memory. The beauty of this is that it is fully pin compatible, so if you have a platform that can take Sapphire HBM, then it will also take Sapphire, so you don't need another platform. And you can boot it without DDR5. Everything can sit in the cache, your application, your OS, your everything, then that's fine. You can run without DDR. You can also run it with DDR if you need more memory. In that case, you can choose between the lazy route, I would say, where the HBM becomes the cache to the DDR, and then the OS will naturally try to identify which data you use the most, and they will put it in the cache. Or you can try and get as much performance as you want. In that case, you use the flat mode, and you just have to decide when you program your application. In that case, you will have to look at it, analyze it, profile it, and decide where you want yourself to locate the data. You locate it directly into the HBM. In that case, it will be much, much more accessible. Or you use it a little bit less and you put it in the DDR. That translates into significant performance increase. Here we are looking at the conjugate gradient. And you can see that on a CPU without HBM, you have a certain performance. And lower is better here. You get about 68% lower power usage if you use just HBM. And that translates into, if you're running AccuSolve from Altair and you run it on 4 nodes of, let's say, Ice Lake previous generation, then you get a certain level of performance, and you can meet that level of performance with only 1 node of Xeon CPU Max, no DDR, and a lot less power consumed. So that's in terms of TCO, in terms of acquisition and operation cost, a significant savings. When we look at the comparison between the previous generation Ice Lake on the left, reference 1.0, and the industry standards here in darker blue, fourth generation Xeon, and in lighter blue, the Xeon Max, then you can see that on lean pack, you're getting about the same level of performance because it's a Sapphire core that is running anyway. And for the applications that are memory bandwidth bound, like Stream or HPCG, then of course you're getting a very, very big performance increase. We are seeing about 4x the performance between Sapphire and Sapphire HBM on Stream, and that's the theoretical performance increase that the HBM is making possible. Again, this is great, but what matters is how does it show in terms of performance on the real applications. So reference here is the Ice Lake Top SKU 8380, and then in dark blue, the fourth generation Xeon, and on a kind of lighter blue, the Xeon Max. And you can see here that the performance gains are from 1.something x to 3x or even 3.7x on real workloads, and that's time to solution. So that's really worth it. So that's for HPC, but that's also valid for AI. And we know that AI does not always require let's say, discrete accelerator. As I said, the fourth generation Xeon processor includes AMX. AMX helps with int8 and FP16 in terms of all of the training and inference capabilities, and they are directly used in the libraries that are uploaded in or upstreamed into the versions of the, let's say, PyTorch and TensorFlow. And here, comparing with previous generations of Xeon or competition, then you can see that it really makes a big difference. We're not talking about a few percent, we're talking here about 20x performance. And you don't need to pay neither the acquisition cost nor the operation of a discrete accelerator. Now, I'm not saying that discrete accelerators are not needed, but when you have various or a very big set of users who have many workloads, you want to have a solution that will work for as many of them as possible without investing too much in it and making it, let's say, not used enough. So in that case, when we get to Xeon Max, you can see here that Crossroads in the US have decided to implement their solution purely on Xeon Max. And I checked the URL, which is at the bottom. You can check yourself. It's public. They have used 0 DDR. So they have decided to run all of their applications only using the HBM memory of the Xeon Max processor. And without any code change, because you don't need to change anything here. You just use faster memory. Then they are claiming 8.6x the performance compared to their previous generation of machine, and it was a Haswell processor that they had. As I said, what is important is that there's a solution that works for all of the workloads, simulation, AI, or anything. And one API is the development environment for that. It will work, as you can see at the bottom, on Xeon Max, on Intel data center GPUs, codename Ponte Vecchio. It also offers tools to run on FPGAs. It runs also on competitive hardware. ARM have provided a solution. ARM A64FX has a version of one API. There's also a version for NVIDIA GPUs, and all this made possible with the implementation of one API by Intel, where you can have a tool that takes CUDA source code and translate it into SQL, which is the language, the portable language that is used here. We see about 90-ish% of the source code being translated, and of course, the rest you have to do it manually, but then you have something that works very, very well. There are a lot of libraries. It's based on open standards as much as we can. That's what we try on doing, not only for hardware, but also for software. So that's why we have decided to use SQL. All of this comes for free in a one API implementation by Intel, where you have the basic version, but you can also have the HPC-specific environment, the IoT-specific environment, and plenty of others in terms of tools that allow you to develop code that will be portable. Portable not only to Xeon, but also to the new Intel GPU that we have announced earlier this year, Ponte Vecchio. Code name Ponte Vecchio, but the name is Intel Data Center GPU Max. So this is based on XE cores, and you can see here that there are 128 of those. Each of them has 8 vector cores and 8 matrix cores, pretty similar to what you find in AVX 512 and AMX, except that here it's called XMX because it will not be 8 or 1 kilobyte per matrix, but it will be 512 bytes, just to match the bandwidth and the memory available. Peak performance 52 teraflops, and 16 links capable of talking to other similar GPUs at about 53 giga transfer per second, so that matches something like north of 800 gigabytes per second. What is important is that we talked about it and we heard about it a lot. The data is big, usually when you want to do something. So here we have decided to go with enough local memory, 128 gigabytes of HBM2E. So that's 8 stacks of 16 gig. HBM2E gives you about, I think in this case, theoretical, about 3 terabytes per second of memory bandwidth. Access to the memory is important, but if you have a good cache, then that's also helping. That's why here we have added a level 2 cache of up to 408 megabytes that gives even faster access to the memory. Of course, on Xeon, and that's what's shown on the left here, on Xeon or Xeon Max, you don't have to do anything. All of the applications run without being updated or ported. And as we always do when we come up with a new generation of processor, but in that case also a GPU, we are doing a lot of software ecosystem enabling. And you can see here a list of the applications that we are working on and that are being ported on the data center GPU Max. Some of them show better performance already than on competitive GPUs, A100 or H100. And we are keeping working on them to make them even more high performance. What choice do you have in terms of GPU from Intel? You will have a PCIe version, about 300 watts, and let's say about 26 teraflops peak in terms of performance. And then you will have a version up to 600 watts that's capable of the peak performance that I showed earlier. And then you can decide how you want to use it. but we are also offering a solution where you put up to 4 of them on a kind of subsystem, which is on the right, and that you can cool. We have seen that in one new solution. You can have 2 CPUs with 4 of those Ponte Vecchios, and you have a direct liquid cooling solution that makes it extremely dense. So how does it perform on applications? On lamps, in that case, you can see that as a reference, we have the Ice Lake processor, the AT380. If you run it on the Xeon Max, then you get 30% more performance. If you run it on Xeon Max plus Ponte Vecchio, then you get 8.2x. And if you don't use any DDR, then you get even faster with up to 12.9x the performance. So one API being used for porting the application, lamps shows very, very good level of performance and is proving very effective. So in terms of approach, we have looked at the workloads. Xeon 4th generation can cover a lot of them. For the memory bandwidth bound applications, then Xeon Max. For the applications that require or that benefit from the GPU, then you have the GPU Max from Intel. And into the future, what is coming? First, Intel is back with and that's public, we are developing 5 manufacturing nodes in 4 years. So at the moment, we are on Intel 7, and that's what the 4th generation of Intel Xeon is on. Intel 4, which is the next one coming this year, will be used for I think no data center or HPC CPUs, but will be used for a client CPU called Meteor Lake. Intel 3 is coming early next year with a new generation of CPU, which is called Sierra Forest, and Granite Rapids, which is the next one. And we have then, after that, the Angstrom era with the Intel 20A and Intel 18A. And for both Intel 20A and Intel 18A, we have already produced test chips in those process nodes. So we are really executing to our plans on this. And this slide is just to show you what has been announced a few days ago. You can see on the left at the top the 4th generation Xeon processor, Sapphire Rapids. It's being upgraded into Emerald Rapids, which is called here 5th generation Intel Xeon Scalable processor, and we've already booted it. After that will come Granite Rapids. We've also booted Granite Rapids, and those are the typical processors that you're used to with what I would call performance cores. But we know also that there are some workloads that benefit from, let's say, simpler cores, and that's the efficient cores that you see on the second swim lane, E-cores, efficient cores. Sierra Forest is the first occurrence of it, and we have announced already the second generation, which is called Clearwater Forest. In terms of GPUs, we have the Flex version, which is more capable of VDI, media, transcoding, and stuff like this, and the GPU Max that I talked about with Ponte Vecchio. And then all of the dedicated AI solutions in case you do AI for a business, you don't necessarily want to run it on a GPU. You might want to run it on a very dedicated ASIC type of hardware like Gaudi. And of course, FPGAs we still have, and we see them being adopted a little bit more as we have now an environment for developing applications for them that is a lot easier to use. So with this, you can see that Intel has a good offering now, and we'll have an even better offering in the future for HPC as well as AI. Thank you.
Any questions for Jean-Laurent?
So the question is, what's the price difference between Ponte Vecchio, MI300 coming, and H100? I would say there are probably price lists that everybody is aware of, but I can tell you that we will be competing very much to make sure that we are price-performance competitive. So we'll price it at the right level. Yeah, so the question is on Gaudi. So Gaudi is an ASIC that is capable of running AI training very, very efficiently because it's an ASIC. Therefore, the software is directly, let's say, implemented into the hardware, and there's no wasted time running something. It's just hardware. So you just get the data through it, and that's how it's very high performance and performance per watt. We can talk about that separately, but that's the difference between a CPU which is fully programmable, an FPGA which is kind of embedding a code into hardware and is a little bit faster, but you can reprogram it, while an ASIC like Gaudi has the algorithms fully into the hardware so that it goes much, much faster. No, so the question is there any competition between GPU and Gaudi? There is not much more competition between those two than between different types of CPUs. You choose the one that meets your needs, and then you just make a decision for your criteria, let's say TCO or time to solution, whatever. So if you are, as I said, running many different workloads, HPC, AI simulation, whatever, then you might want to use CPU and CPU plus GPU. If you do AI training for a living, then you want something that will be doing just that and very efficiently. An ASIC would be a good solution, potentially. There was a question there.
Again, about Gaudi. Is it evaluating the neural network or also doing the back propagation? So it's really for training or more for evaluation of an existing model?
So Gaudi is targeted more at training. If you want to do, so it uses, of course, the techniques of training. If you want to do inference, then there are some other solutions, again, some ASICs that are capable of doing that.
I have a question. I was in a meeting, so I did not follow everything, but I've seen just a place where you showed the power consumption and some of your hardware, and some of them, they're just hitting up to 2.4. kilowatt. And I'm just wondering, I mean, how dense are these? What's the form factor for this product? And exactly, and what's how do you cool them actually? I mean, just what you're expecting from the cooling point of view.
Yeah, so that's the rightmost solution here. As you can see in the middle, each top SKU GPU goes up to 600 watts.
Yep.
If you put 4 of them on a tray, that's 2400,
Yep.
and then you just cool them in 1U with direct liquid cooling. That works well.
That's 2.4 in 1U. I mean, I just like imagine you have
It's even more than that,
40
Hussein.
U rack. I mean, I don't know where it's going to be possible.
So let's be honest. If we go really to what I said earlier, where you have 2 CPUs plus 4 GPUs in 1U, just the 4 GPUs at 2400 watts, plus the 2 CPUs up to 350 watts each, that's 3100 watts. Let's say 3500 with memory and all that kind of stuff. Multiplied by 36 U's, I'm not good at that, but I think that it will be in the range of 150 kilowatts. Yes, it's feasible. We are seeing it. It's super dense. And that brings me to one message that I was not planning to address here, but let's prepare for extremely dense solutions where you can potentially go up to 300 kilowatts per rack. Of course, not a regular rack, but a very specific rack. HP are doing that, Atos are doing that, Lenovo are doing that, etc.
Interesting.
So power, cooling, yeah.
Yeah, that's a big challenge actually, because now if we have a challenge that's going is the power, and what we are doing with the power in the future. I mean,
Exactly.
So that's a big challenge. Yeah.
Thank you.